All right, welcome to day 6. All right, what is the measure of angle ACB? Okay, ACB, we want to know what this angle is right here. Okay, it's not necessarily congruent to this one. Now, BOA is what type of angle? It's a central angle. We'll remember this. Central angles equal the arc it intercepts. So we're intercepting arc AB. So therefore, this arc is going to be 56. However, we want this angle right here. And what type of angle is ACB? If you said inscribed, you're correct. Now it does intercept the same arc, but it doesn't mean that they're equal. Remember, inscribed is half the arc. So if I take 56 and I divide by 2, you're going to end up with 28. So 28 is that angle right there. All right, now number 2, what is the measure of angle X? All right, what is the measure of angle W and what is the measure of angle Z? All right, so here we go. Measure of angle, I like to write these out when there's multiple things to find. All right, so when I look here, we learned this the other day. Here, I know this is the center of the circle, okay, because there's a dot in the middle, so forth. Here, when it's a radii right here, and then this is tangent, then guess what? That's 90 degrees. So I know it just says measure of angle X, but really, I guess X could be either way. So that's 90 degrees right there. Well, same thing right here. This is 90 degrees as well. All right. Well, the question is, what is this thing right here? Okay. I got to find the measure of angle W. Well, let's look here. Now, one of the things is, do you know, this is a quadrilateral right here. Do you know how many degrees are in a quadrilateral? 360. So if I just take 360 and I minus 70 minus 90 and minus 90 again, the other 3 angles, then guess what? I've got it. So 360 minus 90 minus 70. Okay, I get 110. So this angle is 110 right here. But there is another way that we could figure this out. Do you remember the other day when we did the far arc minus the close arc, which is right here? So if I call this X, then this one's going to be like 360 minus X. All right, and it equals the angle. So the angle, which is 70, equals the far arc, which is X, minus, now I'm going to need parentheses, the close arc. All right, divided by 2. Okay, now I got to distribute this minus sign like that. Now I'm going to do a couple things at once. I'm going to multiply each side by 2. So this is 140 equals. Now this X and that X are going to make 2X. Now these 2's cancel, and then I have negative 360. All right, now add 360 to both sides. I get this to be 500 equals 2X. And when I divide by 2, I get X to be 250. Well, what that means is this is 250 right here. Well, what does that mean for this? This is really the arc. That's probably where I should put X, but 360 minus 250 leaves me with 110. Okay, so this one right here, that arc right there is 110. Well, guess what? This right here is a W, is a central angle. And remember, central angles equal the arc. So if that arc is 110, so is the angle. So that's a second way to get that one as well, and using some of the theorems that we did. At first, I used the theorem that a quadrilateral has 360 degrees. All right. And then secondly, you can use that far arc minus the close arc. All right, so here we go. This one right here. Now, here, these are talking about segments this time. It's not talking about angles of arcs, measures of arcs or anything. All right, so here, we're going to do the outside. I'll start with the bottom one first, times the whole. Remember, we add it together. So X plus 7, don't do 7X. The outside times the whole. All right, like that. Now you could plug one side in, plug the other side into Desmos, find their intersection. That's completely fine. I will do this by hand. X squared plus 7X, we got to distribute. Now here when you distribute, X times X is X squared, X times 3 is 3X. 3 times x is 3x, and 3 times 3 is 9. So x squared plus 7x equals x squared plus 6x plus 9. And now watch this. When I subtract the x squareds, do you see how they just go away? All right, now what we can do, solve for x. So those went away. I can also subtract 6x, and I get x equals 9. All right, and that's what I wanted to find. I wanted to find x equals 9. So this one was a nice one where the quadratic part of it actually went away with subtraction once I multiplied everything out. All right, make sure you're reviewing over the circle stuff, know the theorems and so forth, because we're going to move, you're going to see a couple of circles today, but we're going to move away from finding segments and angles and arcs to something else that we're going to talk about. Now, I have this page right here. We're going to be talking about points of concurrency. Now, if you want to watch this is a video that is not me. So if you want to type this in, feel free to do that. But I'm going to go over different points of concurrency. Now, first off, what is a point of concurrency? This is where two or more lines intersect. In our case, we're going to see where three special lines intersect. Now, there are a few things that you have to know first, like what is a median? Some of these things you may have heard before and you have learned in previous math classes, but we're bringing them back up here. All right, so here we go. What is a median? Well, when I think of median, I think middle. So in a triangle, a median comes from a vertex to the midpoint of the other side, like this. And how do I know it's the midpoint? Think middle, like that segment's going to be congruent to that segment. So a definition for it's a segment going from the vertex to the midpoint of the opposite side. All right. Now, this actually has three medians, okay? I can draw it from this one down to here, and you see these are congruent. Here, I can draw from this vertex over to here, and these sides are congruent. I can draw one from here. And we notice that these three segments meet at a point, and this is called the point of concurrency. And this point of concurrency is known as a centroid. So one big thing you need to know is that centroids and medians go together. All right. Now, some things that you need to know is that inside of an acute triangles are when all the angles are less than 90 degrees. The centroid is always going to be inside. In a right triangle, the centroid will always be inside the triangle. And an obtuse triangle, it will always be inside as well. All right, now there are some key characteristics. When you hear median, you hear centroid, you see this picture, okay? The centroid divides the median in two unequal parts. Okay, so, and the longer is always twice the smaller. All right, so what do I mean by that? Okay, so here you can kind of visually see which part is the long part and which one's the short one. The long part is always coming from the vertex to the centroid. And if this is 6 right here, if you know the long part, you take half of it, and then you know that part's 3. Okay, so let's do this again. All right, here, if this part, the short part is 4, how much is the long part going to be? It's going to be 8. Now, there's something special as well. So sometimes what they may do is say, okay, this entire segment is 12. All right, so what are the two small parts? Well, if that entire segment is 12, think about this. The longer part, let's say the shorter part is x, and this one's 2x. All right, well, if I add those together, 2x plus x is supposed to equal 12. So 3x equals 12, and I divide by 3. So x equals 4. So here, the small segment, the segment would be 4, and then 2 times it would be 8. And when I add those together, doesn't it add to 12 right there? All right, so they could do that. And the equation will be the same each time, and you're always basically dividing that whole number, that whole length of that segment by 3. And then you've got the small segment, multiply it by 2, and you've got the bigger one. All right, now another thing about the centroid is the centroid is called the center of gravity. Okay, or the balance point. Basically, if we were to take, say, like a piece of paper, say like this, okay, if it was a triangle, if the centroid was right there and I took a pencil or my finger, I could balance it right here and it would balance on that point, which is called the centroid. All right. Now, angle bisector. Well, whenever you hear bisector, you should think cut in half, and it cuts it equally. Well, it's cutting the angle in half. All right, so let me draw a triangle. It always comes from a vertex. All right, it doesn't necessarily cut these two in half. It cuts the angle in half so that it's congruent right there. All right, so it divides the vertex into two equal angles. Now, sometimes they're going to tell you it's an angle bisector, but sometimes they're going to just show you. I know it's kind of hard to see this right here, but like they're showing you that this angle is congruent to that one. This one's congruent to that one. This one's congruent to that one. So if I were to draw all those, they meet in the middle and they meet at a point called the incenter. So the point of concurrency of an angle bisectors, the three angle bisectors in a triangle, is called the incenter. And no matter how I draw it in any type of triangle, it's always going to be inside the triangle. All right. Well, what does the incenter do? The incenter is the center of a circle inscribed, that means inside, the triangle. And I'm just going to draw a triangle right there for that. Okay. So basically, and you see that this circle's already drawn here. Okay, so this point right here is the center of that circle, and that's called the incenter. All right, and the distance from the incenter to each side of the triangle is equidistant. Equidistant means equal distances. All right, so what that means is when we talk about distance from one point to another, if it's a straight line, and it's going to be a straight line perpendicular, and you see these right angles right here. So this right here is going to equal this segment right here is going to equal that segment right there. And why are they equal to one another? Well, what do you notice it is of the circles? Well, it's the radii of the circle, and that's why those are equal to one another. And these distances, this is at a right angle right here. Okay, so when you see angle bisectors, they meet at one point or they tell you that you have an incenter. You just need to know this right here, that you can draw a circle in the center and the distance from that center, that incenter, to each side is the same. All right, the third type of point, or third type of segment that we want to talk about is a perpendicular bisector. Well, we got two things going on. Perpendicular, what does that mean? Well, it meets at a right angle. Bisector means it cuts something in half. All right, so right here. Now, the other two have to come from a vertex. A perpendicular bisector doesn't. Say like right here. Here, that is the midpoint, and it comes from midpoint to the side at a right angle. So that it doesn't have to come from a vertex. All right. So basically it starts at the midpoint of a side and creates, sorry, a right angle with the side. All right, and that's what we did. And again, it doesn't have to come from the vertex. All right, and you see that right here, okay, this is a perpendicular bisector. It's perpendicular, splits it in half. This is perpendicular, splits it in half. And none of these come from the vertex. They can, but they, in this case, don't. But they all meet at this point, and this point is called the circumcenter. All right. Now, this one's a little bit different. Now, this is an acute triangle. And in an acute triangle, the circumcenter is inside the triangle like you see here. But when it comes down to a right triangle, in a right triangle, it's going to be on the circle. And it's basically on the midpoint of the hypotenuse. Okay, this is going to be the midpoint, so that's going to be end up congruent to that right there. All right, and then if it's an obtuse triangle, it's actually that point is going to be outside the triangle. All right, now the center of a triangle, circumscribe around the triangle. All right, so basically this point right here is the center of a circle. Now this isn't going to be great because I'm going to go outside this box right here. But inscribe means the circle's inside. Circumscribe means the circle's going to be on the outside. So like here, I can draw a circle on the outside of this figure. All right, not a great circle. Sorry about that. All right, and what happens is the circumcenter. So this is the circumcenter right here. All right, the circumcenter. Now that's going to be the center of that circle. I know it doesn't look like it in this picture. If I had drawn it better, it would. But the circumcenter, not only is it the center of that circle that's circumscribed in the triangle, but the circumcenter is equidistant to each vertex. All right, and what I mean by that is this point right here, the circumcenter, if I draw a segment to each vertex, each of these right here will be congruent to each other. All right, it's the same distance from each vertex. All right, and lastly, now, this last one's not necessarily in our curriculum, but I like to teach it just to kind of get the whole thing of points of concurrency. Altitude. And altitude comes from this one does have to come from a vertex. Perpendicular bisector is the only one that doesn't. Altitude comes from a vertex at a right angle. Nothing is going to be equal to one another. So basically, it starts at the vertex and makes a right angle with the opposite side. All right. And like this one right here, vertex, right angle, vertex, right angle, vertex, right angle, it all meets at one point. And this point is called the orthocenter. All right. Now, this is an acute triangle, and we notice that the orthocenter is inside the triangle. Now, if I were to draw the right triangle, I would notice that it would be on the triangle at the vertex of the right angle. Okay, and the obtuse triangle, the orthocenter is going to be outside. Now, I'm just going to write this. We don't know much about this. We just need to know what an altitude looks like and that they all meet at the orthocenter. And that's about it. Our main goal is to understand these top three. So make sure you reread these. And as you start doing examples of it, that you're going back and using this document right here. Okay, so here we go. Let's apply some examples to this. All right, so we're going to do this one right here. Now, NQ equals 6, and I think, do they have that on there? No, they do not have NQ equals 6. So that whole thing's 6. RK, or yeah, RK, they do have that, is 3. PK is 4, and that's on there as well. Now, they do not tell us anything about this. They do not tell us we have what type of point of concurrency we have. All they do is they give us this figure right here. Can you tell what type of points of concurrency? Go back to your chart. I noticed that coming from a vertex, and then these are equal. I don't see any right angles. I don't see any angles congruent. So therefore, each of these are medians, and this point is our centroid. Well, what happens with a centroid? Well, this one, we can figure out all those segments on the inside. Remember, if this segment is 3, notice this is the longer segment because it comes from a vertex. If we take half of it, 1.5, then I have that segment. All right, same thing here. This is the longer segment, 4. So what do I know? Well, I can figure out MK is half of that. That's 2. All right, and then let me get a different color over here. Okay, now they tell me NQ, the whole thing is 6. Well, remember when I did this, the smaller part's X, and then that's going to be 2X. So let's do a little math over here. If I add X and 2X, it's going to equal 6. And when I add that together, that's 3X. Some of you may remember, just divide it by 3, and I get X equals 2. So the smaller part is 2, and so 2 times 2, the bigger part is going to be 4. All right, so here we go. Let's go answer the questions now that we've got a lot of it filled in. KM, all right, KM we have is 2. KQ, all right, that's that segment right there, is 4. LK is 1.5. LR, all right, that's everything. We're adding the 1.5 and the 3, so that's 4.5. NK, all right, that short side right there is 2. And then the last one, PM. PM is the whole thing, 4 plus 2, which is 6. All right, there we go. All right, so they didn't even tell us the centroid. You had to figure that out by what the markings had on the triangle. Now, down here at this one, notice they do tell us it's a centroid. All right, EH is 6, so I'm going to draw some of these in because they're not in there. All right, DH, this one right here, is going to be 4. SM, now that's that whole thing is 24. I'm going to hold off. Okay, so for right now, what do I know? If I know this is 6, how much do I know HR is? Because again, it's a centroid, the same thing that we were doing before. If you said 12, you're correct. All right, DH. Okay, if DH is 4, well, what is HT? Double it, and you get 8 because that's our longer part. Now, they tell us this entire thing is 24. Now, I can set up an equation just like this one, or just think, if that thing's 24, again, x and 2x, if you want to add that together, get 3x equals 24. Or you may just want to say I'm dividing it by 3, so x equals 8. That means the smaller one's 8, and then when I do 2 times 8, that's 16. And if I want to double check, they add together to be 24. So here we go. SH, we found is 16. HM is going to be 8. TH is going to be 8, and then HR is going to be 12. All right, TD is the entire thing. 8 plus 4 is 12. And then ER is the whole thing. 6 plus 12 is 18. All right, so once you start figuring stuff out in your figure, you can actually then, it's easier to answer the questions. All right, so here we go. Well, guess what? We have another one. We can do a lot with centroid. All right, so if you want to, go pause this. I'm going to go solve some of this as well. these aren't necessarily the same thing. Now, if they give us UQ, UQ is this part is 6. All right, what is US? Well, US is double that. That's 12. And then what's QS? Well, if I add it together, I get 18. All right, now let's go do the other part, UT. Now notice UT is the bigger part right here. That's 3. Okay, so UV is the smaller part. Take half. That's 1.5. And so TV, when I add it together, I get 4.5. All right, and then UW. UW is 2. That's the smaller part. So I know this part, RU or UR is 4. And then WR, we just add those together and we get 6. So hopefully you got those correct. All right, because it's the same thing we've been doing. Now these are a little bit different right here. Now find the value of X using the concurrency of angle bisectors. Now, what is that name? Keep going back and forth. Angle bisectors are in center. All right. And one of the things is, remember, you can draw the circle in the center right here. All right. Anytime you have an angle bisector. So that point where they meet, these are the radii, and these are going to be equal to one another. So I can find X by setting this equal to one another. So the X equals 3 in this case. All right. Same thing again. All right, here I have angle bisectors. They meet at a point. I can draw the circle in the center. And both of these are radii, so these are going to be equal to one another. And think about this. In center, I can draw a circle in the center. Go ahead and subtract 2x, and we get x equals 5. And last one, again, angle bisector. These are all kind of the same type of problem. I can draw a circle in the center. These are both radii, the distance from that in center to each side. And notice that it's at a right angle. And so I set x plus 2 equal to 2x minus 3. Subtract x, and I get 2 equals x minus 3, and then go add 3. Okay, so 5 equals x. All right, here we go. Now, we got a couple more problems right here. Point I is the in center. Okay, so when I hear in center, think angle bisector. We actually do see it in this right here. It says IU, okay, that's this segment right here, is 2x plus 15. Draw it in. IT, which is this one right here, is 3x. Well, what do you notice? They're both radii, so they're going to be equal to one another. All right, now subtract 2x. We get 15 equals x. Now, notice this isn't find x. This is find is. Is is this right here. Well, guess what? It's another radii. So I can plug that in right there and say 315 equals 45. So 45 is my real answer right there. Okay. All right. Okay, we're going to get to this next one in just a second. All right, and we're back to finishing this right here. Now, use the properties of angle and perpendicular bisectors. Okay, let's review this. Perpendicular bisectors, what's its point of concurrency? Circumcenter. This is the one we can circumscribe a circle on the outside. Now, I might not need it for this problem, but remember all these things whenever you hear perpendicular bisector or circumcenter. All right, according to the diagram, what are the lengths of PQ and PS? Now, remember I told you perpendicular bisectors do not have to come from a vertex, but when they do, it's actually going to be very special. When it does, it actually means that this segment right here, since it's coming from a vertex, is both a angle bisector. So these angles are going to be equal to one another. It's a perpendicular bisector, which is stated. It's a median as well because it comes from a vertex and hits these are equal. And it's also an altitude because it comes from a vertex at a right angle. So it's all 4 of those things combined. Well, what happens is when it does that, these 2 triangles are actually going to be congruent to one another. So here, according to the diagram, where the lengths are PQ, all right, PQ and PS, well, if that's 10, this is 10. All right. Now, how is PR, this right here, related to SPQ? SPQ. Well, here it is an angle bisector. So that we can find the value of n in number 13. And we can set these equal to one another. All right. Here I can subtract 5n. Now be careful, that is a negative 20 equals negative 2n. And then divide by negative 2. So n equals 10. So we just found the value of n. All right, and lastly, let's find angle SPR, SPR, and QPR. Well, these are congruent. So all I need to do is plug that in value I just found in, and I get both of those angles are going to be 30. If you want to double check it, you can plug in 10 here. 50 minus 20 is also 30 as well. Make sure you review, make sure you know this chart right here, okay, that we filled out, that we've got right here, okay? You need to know all the different points of concurrency, specifically these right here, okay? Know about the segments, know about the circles, know when the vertexes are equal to one another. Knowing the background of all of these will be very, very important when you're doing points of concurrency. And as always, if you have any questions, make sure you ask your teacher.